This ordinary-looking performance shirt hides a second life that began somewhere almost nobody would think to look. The starting point is not cotton, wool, or fresh coffee beans. It is the wet residue left after brewing. How does this dark café waste cross an entire factory and return as fabric you can actually wear? The journey starts with spent grounds collected in sealed containers, keeping the wet residue separated from ordinary trash before processing begins. A single batch can contain residue from thousands of brewed cups, so traceable handling matters before any textile step begins. Paper, plastic, and foreign debris must leave first, because the next machines need one consistent feed instead of mixed café waste. Now the waste stream is clean enough to measure, but it is still far too wet to enter a fiber-making process. Each incoming tote can represent hundreds of brewed cups, so weighing converts scattered café waste into a measurable industrial batch. The screen removes oversized fragments without changing the coffee itself. It simply creates a more uniform stream for the press. Human inspection still catches irregular pieces that mechanical screening may miss, especially lightweight fragments riding on top of the wet grounds. Nothing here is allowed to spill onto the floor. Each batch moves in closed containers or guarded conveyors from one station to another. Fresh spent grounds can hold roughly 55 to 65% moisture, making water removal the first major engineering problem. But drying this waste is not the strangest step. The real transformation begins only after the grounds become a controlled powder. Mechanical pressing removes free water before heat is added, reducing the energy needed later and giving the dryer a steadier feed. The pressed residue behaves more like damp soil than slurry, a simple texture change that makes controlled belt drying much easier. Across the hall, separate presses converge on one drying line, turning scattered café residue into a single continuous industrial material stream. The collection stage is over. From here, moisture, particle size, and heat will determine whether this waste can become textile feedstock. An even bed matters because thick piles dry slowly while thin patches can overheat, so the feed gate controls depth before heating. The dryer may remove more than half the incoming water mass, shrinking a wet waste stream into stable feedstock. After drying, the residue flows instead of clumping, a small visual change that makes the next screening and milling steps possible. Cooling the dried grounds is like resting baked material before milling. Stable temperature prevents unnecessary heat from following into the next machines. The dry screen creates a narrower particle range because oversized pieces would grind differently and make the final additive less consistent. A contamination check protects both the mill and the later spinning equipment, where even a small hard fragment can damage fine passages. Micronizing can reduce dried coffee particles to tens of micrometers, creating far more surface area for later blending. At this scale, consistency matters more than appearance. Uneven powder can create weak spots when the blend is later pushed through spinnerets. The residue now looks nothing like wet café waste, yet it still cannot become yarn. Its surface must be engineered next. Thermal treatment can exceed 200 degrees Celsius, changing surface behavior while the powder stays enclosed inside the processing drum. The important change is microscopic, not dramatic. Porous structure is intended to help interact with odor molecules during wear. Once treatment ends, technicians cool and isolate the additive so each downstream batch receives the same controlled powder feed before compounding begins. A fraction of additive blended into polymer can influence an entire filament because the particles become distributed through the yarn. Two feeds must stay controlled because too little additive weakens the intended function, while too much can disturb spinning. Can waste-derived powder survive melting and extrusion once it meets conventional textile feedstock, or will the blend fail before spinning? One extruder can blend kilograms of feedstock each hour, distributing coffee-derived particles through molten polymer before pelletizing here. The blend has crossed from powder into a unified solid material, but it still needs a shape that spinning machines can meter reliably. Uniform pellets give the spinning line a predictable feed, turning a complicated mixture into thousands of nearly identical processing units. The temperature looks stable.
Yes, within the optimal range.
Continue routing the master batch bins to storage. The impossible-looking part is complete. Café waste is now inside a textile-grade feedstock. Next, the spinning feed looks more like plastic grain than textile fiber, yet those pellets are only minutes from becoming continuous yarn. Dozens of fine streams solidify almost instantly as cool air removes heat, transforming molten polymer into continuous. The filaments are thin but not finished. Their molecular structure still needs drawing before the yarn gains useful strength and stability. Drawing can stretch fresh filaments several times their original length, aligning structure and increasing strength before final winding. Every filament now has a destination, from spinneret through cooling and drawing directly onto a take-up package without loose yarn touching the floor. Texturing adds controlled bulk and stretch, changing smooth filament into a yarn better suited for soft performance fabric and everyday clothing. Under magnification, the yarn looks like ordinary textile fiber. The coffee-derived component is dispersed inside rather than sitting as loose grounds. Line turns continuous filament into manageable yarn packages, each ready to move directly into knitting without exposing loose material to the floor.
The density of the equipment allows for unparalleled efficiency.
Understood. I'll recalibrate the tension. Before knitting, technicians check uniformity and handling behavior because a weak or irregular yarn can create visible defects across an entire fabric roll. What began as dark, wet residue is now stable yarn. The next machines will decide whether it feels like clothing rather than industrial filament. The heavy machines are behind us, but can this engineered yarn now behave like the soft fabric people expect from clothing? Knitting converts one-dimensional yarn into a flexible surface, building thousands of interlocking loops that give the shirt stretch and softness. This is the payoff. The same waste stream that arrived as wet grounds is now a continuous fabric moving straight off a knitting machine. Keeping the fabric supported from machine to roll prevents stretching and wrinkles before finishing, so nothing hangs loose or touches the floor. Finishing treats fabric like final tuning on an instrument, adjusting feel and stability without undoing the structure created during knitting. Secure the roll, team. Finishing controls hand feel, dimensional stability, and surface behavior, turning raw knitted fabric into material ready for precise garment cutting. A single fabric roll can extend hundreds of meters, so one missed defect may repeat across many finished garments. Human hands return at the final assembly stage, guiding panels through sewing machines where fit, seam alignment, and finish become visible. The textile is now a shirt, but appearance alone is not enough. Testing must decide whether the finished garment meets its intended performance. Quality control starts with visible construction. Seam alignment, fabric defects, dimensions, and finish are checked before any performance claim is considered. Tensile testing applies a measured pulling force until a limit is reached, exposing weaknesses hidden inside apparently perfect fabric. Dimensional stability matters because a performance shirt that shrinks unpredictably after washing fails long before odor control can become useful. Odor performance testing compares treated fabric with control material under standardized conditions, separating measurable function from simple marketing language. Only approved garments leave this room. Now the factory story ends, and the everyday life of the shirt begins outside these walls. One packing table can prepare dozens of shirts per hour, but every garment still moves through the same controlled handling steps. Finished shirts are grouped into plain cartons, supported on pallets, and routed toward loading without breaking the controlled material flow. At industrial scale, dozens of cartons can leave one dispatch lane each hour, turning a laboratory idea into everyday inventory. Every vehicle has one job: move approved garments away from production, through distribution, and towards stores where the factory itself disappears from view. After leaving the factory, will anyone looking at this ordinary shirt guess that its material journey started with wet coffee residue? After more than a dozen major process steps, the finished shirt still gives almost no visual clue that coffee waste was involved. Because the coffee-derived additive is dispersed inside the yarn, the buyer feels ordinary fabric rather than loose particles on the surface. Wearing the shirt feels as ordinary as any daily garment, even though its material journey passed through dryers, mills, extruders, and spinnerets. Now the ordinary shirt looks different, because you know the dark residue at the beginning never really disappeared. It changed form.